First of all, I would like to thank the organizers for inviting me. It has been very pleasurable days here. Finally see season changes and things like those. Anyway, I'm going to be presenting work we have been doing with Yelchin, with Yelchin FNDF in collaboration with students and postdocs and some collaborators from Texas A&M since 2009, more or less. So my affiliations are basically, I am the co-director of the Center for Numerical Porous Media, of which Yelchin is the director at KAUST. And I'm also affiliated with Applied Math and Computational Science as well as Earth Sciences. So I try to do things that are in between these fields. So the drivers of our problems are basically, we have to model, for example, reservoirs. Can be oil reservoirs, which in Saudi Arabia produce 97% of the GDP of the country, something like that. Which you have samples that are in the order of a meter, in the sense you can go and draw a sample from the rock. And you have features that in the scale of nanometers and micrometers that affect the flow over the overall scale of a reservoir. And then you have reservoirs like the gigantic reservoirs they have in Saudi Arabia, which have 500 kilometers by 100 kilometers by 1 kilometer depth. And that's a single reservoir, and they have several of those. And same thing here, you see an outcrop in another area in which you see the scale of the outcrop, the details of a micrography taken from one of the samples, and the scales of a fracture. So this is what's going to be controlling most of our problems. So basically, multiple scales that have to be taken into account their effects appropriately when you try to understand how a reservoir is going to produce, but to do so is impossible by modeling everything, so we have to do some kind of model reduction. So as I said before, we'll have things like fractures that are going to be mostly reduced objects of lower dimensions, so it can be lenses, or shale barriers, in the sense of you have these barriers that are very thin, but can have several orders of magnitude lower permeability and can totally obstruct flow. So, well, modeling everything would incur in humongous computational costs. So our driving force is try to model these kind of things when you have to basically understand, for example, where should you put your next well in a reservoir? Or in Saudi Arabia, which actually water is 5 times more expensive than gas, you have to decide how to get water back into the aquifers and how to extract it as cheap as possible. For example, you may not know, but Saudi Arabia exports wheat and milk, but both need quite a bit of water. So they're extracting water from the aquifers to produce that. So our goal basically is to be able to derive models that are accurate in the sense that will give the trend of the global system, while their computational cost is going to be insignificant, in the sense of our ideal goal would be to have computer models that can be run on cell phones. Obviously, we're not there, but at the end of the day, the guys who are running these oil pumps will not have extraordinary compute power, and they will want to make decisions, informed decisions based on simulation, and that's what we try to do. So we try to capture the relevant dynamics, have as small error as possible. Basically, the error is going to be get 1 or 2 digits at most of the behavior. We don't want machine precision, but to do so, we have to control errors everywhere, and I'll show you how we do that. And computational efficiency is our goal. So at the end of the day, what we have is either we can do porous scale models and homogenization, like what Andrew was showing, and we can go to geocellular models, as we were showed today before on this randomized homogenization. But at the end of the day, we want to get coarse scale models in the sense of we can do Darcy flow, for example, if you're doing flow in porous media, and more importantly, input-output models that, given an input, produce an output that is correlated with what would be a full model, but at low complexity, low cost. So what we try to understand is how can we select the appropriate model, and how can we transfer uncertainty, and how can we transfer, for example, how can we use these reduced order models to optimize performance or improve our understanding of how a well is going to work. So the geological models that we work on are, for example, a reservoir that has a lot of seismic data, has production data, has all the logging results of the different wells that have been placed. And what we have to do is try to understand how data can be assimilated and how we can do history matching, if possible, in real time. And again, history matching here, we are not trying to do history matching in the sense that it's going to be an excellent forecast. But by optimizing the history matching to the date that we are looking at, we can get better predictions of how the behavior of the reservoir is going to be. So the fact that forecasts with good, accurate history matched reservoirs do not match the future performance does not mean that we should not try to get accurate history matched data. So we are developing these kind of things. Just as a side note, in NumPOR, this Center for Numerical Porous Media, what we try to do is leverage the fact that we have all this knowledge, for example, from geological applications, driven by oil mostly, to apply the same kind of technology. Obviously, we have to adapt the fact that now we're going to, for example, deal with fibers and how particles are going to attach to fibers that are electrostatically charged, how these particles are going to clog the filter structure, and then the whole model and how we transfer information. We leverage that, and we can reuse a lot of algorithms, 50, 60, 70%, in applications that are on man-made materials to geological applications. So this is kind of a side note. And for example, when we try to optimize well placement, for example, what we have to do is basically put the input parameters that we think we have on the model for data assimilation, for well placement, do a full-scale simulation, and then if we want to do optimization, we may want to compute Jacobians and do adjoint models, and doing this is a very expensive process if we have to model everything at full scale. So what we end up, this is basically our driver, and our goal is that we have reservoirs that actually this number is already old in the sense that we had a reservoir, an upstream symposium at KAUST this weekend, and they were already talking of reservoirs which have reservoir models which have between 10 billion to 100 billion degrees of freedom, and do this in a matter of days. So I'm missing basically 2 zeros here to be comparable to the numbers that they are thinking right now. And our goal is basically with a couple hundred degrees of freedom, be able to get outputs that are comparable. And in the sense that are comparable is mostly the quantities of interest that we have, how do we match them? So how do we go about it? Basically, we do 2 kinds of model reductions. We do what's known as, what we think of as local model reduction, in the sense that we have a fine scale that resolves everything, including porous scale simulations, and we have to transfer that information to coarse scale simulations. And we can do that from using homogenization, numerical homogenization, upscaling. Also doing multiscale model reduction, as in multiscale finite elements, generalized multiscale finite elements, and things like those. And then we also do quite a bit of work on modal analysis, in the sense of we get a full model and we try to derive by modal analysis using proper orthogonal decomposition, dynamic mode decomposition, balanced truncation, do input-output relations between what the parameters we put into a model and the outcome that the model has. So as we have seen several talks in this workshop, basically, if we have scale separation, we can look at inclusions, and we can come up with models that homogenize these inclusions and give us a parameter that we solve in a global scale problem. In many applications that are relevant for engineering, we don't have just inclusions, we also have structures that span several elements. And at the end of the day, what we would like to have is a model, a way of computing the structures that need to be modeled, and a background that includes the inclusion effects. And that's what we try to achieve with multiscale finite elements at the local level. So, for example, if we do have scale separation, and for example, we have periodic structures, or we can do a cell analysis, we can basically do homogenization. I'm not going to go much into this because it has been explained, and this is just to give an idea. So then we can compute, given these local problems that we can solve, we can compute homogenized parameters that can be a scalar or can be a tensor. And then we have bounds that tell us how well the solution to this equation with oscillating coefficients and our approximations by solving this Coarse scale is controlled given the problem size. So the way we do this is, for example, if we have an image doing numerical simulations, is we would put particular boundary conditions on this problem and solve for these coefficients, these homogeneous coefficients. And at the end of the day, what boils down to is that we'll end up putting as many degrees of freedom as cells that we have in the domain. 2 degrees of freedom if we have a 2D problem, 3 degrees of freedom if we have a 3D problem. But as previously mentioned, this is not enough for many applications. So what we have to derive is a way of capturing these structures and remove these local features. So the way we do that is using multiscale finite elements. And the idea behind this is that basically what we want to do is represent our solution on a basis, and the basis is going to be such that solves local problems given particular boundary conditions. And let me, for now, skip the idea of boundary conditions, and you can think of this as being, for example, in the simplest model would be linear finite elements, like linear on this coarse mesh, and then you do minimum energy extensions of the boundary conditions into the domain, and you solve that problem. And what you get are basis functions that look like this, and on these basis functions that you try to solve the problem. This idea was initially proposed by Babushka and Osborne in '83, then Tom Howe developed it with his students, in particular with Yelchin FNDF. So the way we do it is mostly by Galerkin substitution, and what we think of is we get these basis functions and we try to compute the coefficient by doing integrals. So that's how we solve these problems, but we have developed also, and here's the royal we, the community has developed methods for doing finite differences, finite volumes and mixed finite elements for these kind of ideas. So in the end, we need to basically, we have this local multiscale approach in which we basically end up solving for features on these finely described material parameters that depend only on a few degrees of freedom, but these few degrees of freedom are parameterized by some boundary conditions. That is, we have this basis function is described on its domain on the fine mesh. So any evaluation that we need to do of this basis function or its gradient or anything like that has to go through the coarse model into the local region by extension, and then we have to evaluate everything on each of the degrees of freedom, which tends to be fairly expensive anyway. It scales like the cost of the fine mesh. So we are trying to address this shortcoming too, that is, well, shortcoming. We're trying to address this issue. Could we evaluate at the local level these quadratures, that is, for example, the basis function, the mass matrix, or the stiffness matrix, that is the gradients of the functions, at a local level without having to go to every single one of the fine mesh cells. So by solving these local problems, then we can solve snapshots of the global problem, and from these snapshots we will derive our global approximations for input-output. So for example, to give you an idea how these things look, if we have these, let's start with this one, which is simpler. If we have these inclusions that are periodic in some sense, and we put the appropriate boundary conditions to the element, what we'll end up extracting is something that looks like a homogenized coefficient. At the end of the, similarly, if we go and tackle this problem and apply the same ideas of multiscale finite elements, what we'll end up retrieving from the solution of local problems is something that captures the global features that span more than one element in some sense, and all the fine scale features are removed into the homogenized coefficient. And how to do that relies mostly on the eigenvalue problem we solve locally to obtain the fine scale basis functions. And it's in this one, yes. So at the end of the day, what we end up doing is, if you, for example, look at this problem, and this was your domain of analysis. If you did the Rayleigh quotient as is done in multiscale finite elements, and then you grabbed each of the basis functions that you retrieved and multiplied by a partition of unity, what you would find here is that the standard method will give you 6 basis functions that you need to add to a problem. basically one for each of these elongated structures and one for the inclusions, one for each of the inclusions. If you switch the eigenvalue problem from doing the standard mass matrix and change the mass matrix to a weighted coefficient, what this problem will give you is basically only two structures. And this is what was shown here, that most of the local features have been removed and only the global features are kept in the method. And once we have these local eigenfunctions, what we end up doing is we multiply each of these eigenfunctions with a partition of unity functions that we use to describe the method, and this is a set of basis functions that we use to span the global problem. So what we'll end up getting in this case is not only one basis function per degree of freedom, but as many basis functions as we need to capture all the small coefficients that are in the system. So as I mentioned before, if we have to solve this problem and we simply put linear basis functions that was initially done, we'll end up getting local problems because the boundary conditions of these do not match. So putting just linear basis functions here will induce this ringling effect on the boundaries of the elements. So basically, we can avoid that by solving the local eigenvalue problems that I was mentioning before. But also, people have been working on removing these by doing oversampling. And this was work done by Tom Howe and more recently by Antoine. And so what you end up doing is basically you end up solving a local problem, but now that does not include your element that you're trying to analyze, but rather you extend your domain outside the local block. So initially we were having only the block K, and then we have basically extended to the oversampling domain. And what we do is we solve either the eigenvalue problem on this domain, or you put different boundary conditions on this problem, basically 1 and 1 on each of the degrees of freedom, and you solve as many degrees of freedom, as many problems as you have degrees of freedom on the boundary. And in this oversampling domain, you basically solve for your local basis functions. So this kind of idea has been used, as I said, so you end up putting boundary conditions on the block, but these will produce some effects, some ringling effects on the boundaries because the effects don't decay fast enough, so oversampling removes those ringling effects. So the original idea for doing oversampling was to just put 1 in each of the degrees of freedom and 0 on all the others and solve all these eigenvalue problems, and then on these snapshots that are each of these degrees of freedom, find the basis that you want to keep. What we have been doing more recently has been, rather than doing this, use ideas from randomized linear algebra that are used for computing fast singular value decompositions to put values on the boundary of the oversampled domain that are independently sampled Gaussians. So what ends up happening is that with this, which is actually, this is the paper, the most recent paper of all the work I'm going to be presenting. But I put it here because it makes sense in the context of what we're doing. So what you end up doing is you end up putting on all the boundary independent random numbers. And what we noticed was that as it happens in fast singular value decompositions, we can prove, and this is proven in the paper, that, for example, if you want to retrieve 4 singular values or 10 singular values in your domain, it suffices to take, say, 10 plus 4, 14 different boundary conditions on problems that have dimension basically 1,000, and you can still retrieve a fairly accurate representation of the local singular values and with the singular values of the local eigenfunctions that you need to put in your global problem. And what we have obtained is basically we first observed it numerically, and then we were able to prove it theoretically, that by doing these randomized boundary conditions, we can basically preserve the convergence of the generalized multiscale finite element as if we were doing this forcing on each of the degrees of freedom on the boundary. Since we have also refinement strategies, if we need to refine, say we realize that in this domain we need to add degrees of freedom, we can evaluate, say we want to add one more function. What we have found is that we only need to add 3 more vectors to a system. That is 3 more randomly sampled boundary conditions. And with that, we will be able to find 1 more extra function on the rest of the residual. So it's a fairly cheap way of both finding the first set of basis functions and then adaptively refine the discretization on each of the blocks. So the way we think of the problem is similar to the way people that deal with optimization of systems, that is dynamical systems. As an input-output problem, basically we first look at what is the offline cost, which is, for example, in the offline cost we would consider computing all these local basis functions, which are problems that can be computed fully in parallel and can be, in many instances, we have found that we can compute them irrespective of a parameterization, in the sense that as long as we know we are given, for example, the distributions of regions that have coefficients that have jumps. We can compute for a set of jumps these basis functions and then have perturbations of the region in which the localized jumps happen, as well as the values of the jumps, and we still have fairly robust coarse basis functions. So we compute basically offline all these basis functions, and at the end of the day, what we obtain is a reduced space on which we compute the coarse problem, and the way to transfer information from the coarse to the fine and from the fine to the coarse. And then we use these operators and the spaces in which these operators are defined to, on the fly, project the coefficients that we are given for a new parameterization. This could be boundary conditions or a new realization of, for example, permeability distributions. And then for each region, what we will do is project onto the local basis functions that we have retrieved in the offline case to compute the online values of the multiscale finite elements. Well, what that is that we avoid computing new eigenvalue problems on the fly. And then we solve for a coarse scale. And if we realize that we are lacking information, we can do this randomized sampling and improve the resolution in the domains that we have noticed that the error is large. And more importantly, if we can rewrite the problem as parameter independent, we don't even need to do this update of the basis functions. We can directly use the offline basis functions for different sets of boundary conditions or different sets of forcings or parameterizations of the problem. So, So as before, what we end up doing is in the offline problem, what we work is to derive an eigenvalue problem that will allow us to bound with the eigenvalues that we solve, the operator that we end up doing in the global scale. And so what we end up doing is we end up defining these eigenvalue problems depending on the discretization that we're using, that is if we use continuous finite elements or finite volumes or mixed finite elements, the smoothness that we can expect mostly in the coefficient jumps. And from that we define the local problems that the local eigenvalue problems that we end up solving, which are these offline problems that basically model what I showed before, which is this coefficient that masks the local inclusions and captures the global features, and the stiffness where the coefficient is the fully resolved coefficient. And what we do is we end up doing, again, in the offline case, we end up finding all the dominant eigenvalues which are correlated with the smallest coefficients in the problem. So another part that is tightly related to this, but is something that we had to develop and implement independently, is in some sense you can think of this first part as an intrusive way of doing model reduction, in the sense that we have to go and change the discretization, we have to go and change the way the operators are built. And then we also work in non-intrusive ways of doing model reduction, in the sense that what we try to do is use, for example, it could be the coarse problem that from the multiscale problem I showed before, homogenized coefficients, or the full fine scale problem. We produce many, given certain inputs, we produce outputs. And then we try to project on these outputs, on these output vectors, these snapshots, reduced order models, which mostly have been proper orthogonal decomposition or dynamic model decomposition algorithms. And a schematic representation of this is basically we have inputs, and what we will do is we do the fully resolved model. And from this fully resolved model, we will collect outputs. From this collection of outputs, we will apply basically singular value decompositions for both proper orthogonal decomposition or POD or DMD. And depending on the method, we'll end up doing different uses of a singular value decomposition. But at the end of the day, what we can then try to obtain is a Coarse scale representation, a global representation that only links inputs to outputs, and again, with some control of the error. So the two modes that we have, the two ways of doing modal analysis that we have been using have been mostly proper orthogonal decomposition, which boils down to given a subspace of snapshots. The proper orthogonal decomposition, what we will try to do is find in these snapshots the ones that, given a certain set, say you want to choose 10 snapshots, a subspace of dimension 10. These are the snapshots that are gonna minimize the error of the maximum distance of what's not represented in this subspace. So basically, it's an n-width idea. And at the end of the day, what we end up picking are the most energetic modes, which, for example, can be seen here. That, for example, if we try to do basically a water saturation and oil pressure model, what we will do is we'll pick all the snapshots of the water saturation, all the snapshots of the oil pressure, and decompose them into singular value compositions and pick the ones that contribute the most energy to the system. And as is common in practice, basically decay of the singular values is very fast, so very few singular values will reproduce fairly accurately the energy included in the snapshots that you took. And although POD is a widely used technique, one of the things that for me is a weakness is that it's not that good at capturing the dynamics of the system once you leave the snapshot space that you have. And in that sense, DMD, dynamic model decomposition, is a better tool. But anyway, this is very easy to use. There are a lot of tools that can do it. So basically, it's very easy to link different codes using this kind of technology to do global model reduction. So the next idea is basically dynamic model decomposition, which basically, again, what we end up doing is we compute solutions to a system, and then basically try to project onto a subspace of this system. But the main difference here in the idea is that you basically take powers of the eigenvalues, which is basically what ends up being is that you end up treating these snapshots as being a Krylov space. So yes, it's here. So basically, a simple way of thinking of this process is that what we'll end up doing is using the ideas of a Koopman operator. That is, we have a nonlinear process that produced all these solutions. And what we'll try to do is get the eigenstructure of a linear operator that can reproduce these different snapshots. And the basic idea is that if you think of this as a Krylov space, you can think of that you get snapshot 1. And then snapshot 2 is simply the operator applied to snapshot 1. Snapshot 3 is the operator twice applied to snapshot 1, and so forth. So now you treat these snapshots as being the recursive application of the same operator. And what will happen now is that if you take a subspace of dimension 10, what will happen is that the choice of eigenvectors and the projection of this onto this space is not going to be the one that contains most energy. So it's not going to be an n-width, but rather it's going to be the way the last snapshot is reproduced by the previous ones that you have chosen. And so So what this allows you to get is basically a dynamic structure that is much better reproduces the dynamics of the whole system. And I don't have an example just now. I'm going to show it a little bit later. So basically, these are the two ways that we do input-output modeling in this framework. In addition, in conjunction to doing fully resolved schemes or generalized multiscale simulations or any other discretization that we might want to use. So for example, the first problem would be, the first problem that we have looked at has been single-phase problem in compressible flow with heterogeneous coefficients. And what this is the forcing. That is, we apply forcing on the domain, and we want to solve this problem, given that we may have high conductivity inclusions or low conductivity inclusions. The dynamics of these two systems is fairly different. And the main difference is that when you have low conductivity inclusions, if you have a source applied there, that is, if by mistake someone put there a well, the behavior of the system is very, very different. If by mistake you put a well here, what will happen is that this will saturate very fast, and then the diffusion from the boundaries of this is smooth, and everything works fine. So the dynamics of these two processes are slightly different, but the idea is that we parameterize all the problems as follows. Background is 1. The coefficient that is in inclusions can be eta, and eta can be 10 to the 6 or 10 to the minus 6. And these are the kind of coefficient jumps that we have to deal with, because these are kind of coefficient jumps that the oil industry wants to use in their simulations. So the way one would go about this is we would use, say, a finite element discretization, where we simply solve. So we would multiply by a weighting function. We would obtain the mass term, the diffusion term, and the forcing. These are just written this way. And to advance to time n+1, we would basically have to invert an implicit scheme, backward Euler, yes, backward Euler. We would have to invert this matrix and apply the time evolving scheme. And this would be very expensive if we have to resolve everything. So the first thing we do is basically we apply generalized multiscale finite element ideas, which is basically we construct these operators that allow us to go from the fine scale to the coarse scale, and basically use only coarse scale degrees of freedom, where at the end of the day what we want to have is a number of degrees of freedom, NC, which is much smaller than the fully resolved scheme. But this is still too expensive. So for example, some of the cases I'm going to show later on the SPE, the Society of Petroleum Engineers 10 test case, just the geometry requires something like 2 million degrees of freedom. With multiscale finite elements, we can get fairly accurate simulations with 100,000 degrees of freedom. But solving a non-linear partial differential equation with 100,000 degrees of freedom is still fairly expensive in 3D. So this is not enough. So the next thing we put is on top of these schemes, we basically do this projection onto input-output modeling parameters of proper orthogonal decomposition or dynamic mode decomposition, where the snapshots are built on the core space. So again, the idea here is fairly simple, which is basically our final reduced order model is going to be the projection of the core scale finite element, generalized multiscale finite elements onto a subspace given by these modes. And in the end, we end up getting this reduced order model, which could be 1,000 degrees of freedom, that give us a sufficiently accurate representation of the overall behavior of the system. So as I mentioned before, the SP10, for example, this case would need in the order of 1 million degrees of freedom to be solved, resolving all the features of the flow. We used a generalized multiscale finite element, which gives us 100,000 degrees of freedom to reproduce it. And then with these 100,000 degrees of freedom, we can reproduce the dynamics at very, very long times within 10% error or 5% error with 100 modes, global modes, or 150 global modes. But again, as I mentioned before, when we compute these mixed finite elements, we have to go from the coarse mesh to the fine mesh. And whenever we compute these global modes, we go from the mode to the coarse mesh, from the coarse mesh to the fine mesh. So the evaluations at the end of the day of computing a residual or computing a nonlinear mobility or something like that still scales like the number of degrees of freedom that you have in the fine mesh, which still is fairly expensive. So, and the way industry, and here industry is mostly oil industry, which is where we have been looking most often, the way they deal with this is what they called, I don't remember anymore, it's something like linear interpolations of coefficients, which is which basically boils down to you get a linearization of your operator based on some samples. But it's very hard to prove anything on this other than the fact that in many cases it works, and in many other cases you have to tweak it to make it work. So what we end up choosing to do is basically use nonlinear projections and use empirical interpolation ideas to reduce the cost of evaluating the residuals, even for the reduced order model, but even for the generalized multiscale problem. So the way we go about it is basically we think of first, we applied it to a global problem, so just standard ideas of discrete empirical interpolation work. So standard DEIM would work in this context, which is we have to treat, say, for example, the mobility everywhere in the domain. So what we get is samples of the mobility given the coefficients, the solution values that we get over the whole domain. And we use these samples to compute where in the domain should we evaluate this to attain a certain accuracy. And the way, so as I mentioned, what our goal is to obtain a reduced set of functions that we can use global vectors to compute this by evaluating it at some points and using these nonlinear interpolation ideas. And so what we end up doing is first form a snapshot space of computing several possible values of these nonlinear functions, and then apply POD to these nonlinear functions to get the most energetic modes, and then a simple greedy algorithm to that wherever the maximum of one of these eigenvalues is where we're going to evaluate first. The first eigenvalue, the maximum of it, we evaluate there. And then the difference between the first and the second is our residual. And at the maximum of that is the next point, and so forth. So the algorithm, basically, what this algorithm is saying is what I just said, which is basically we get a singular value decomposition of the snapshots we obtained of the nonlinear function. And then we simply get the first snapshot that contains the most energy, and we evaluate at its maxima, the first point, and then we compute the second one, take the difference between the first one and the second one, compute the residual, the maximum of the residual, and so forth. This is basically a paper of Sorensen in 2010. Basically, this algorithm is directly from their paper. We didn't change anything here yet. So when we apply this to our multiscale problems, basically what we can do is we can go and compute the global modes that we have used, either POD or dynamic mode decomposition, and evaluate them at, say, 20 positions, and the 20 positions are these red dots over the whole domain. And what we can see is that if we want to evaluate these DEIM points, basically with 200 points over the domain, we obtain an error of 10 to the minus 4 on the residuals and the Jacobians of the system. So, for example, to give you an idea how this works, is that we need to use, basically, to compute the mobility, in some oil problem, we would need to compute the pressure and the saturation. And so the mobility would be given by this function. So what we can do is basically compute at some points, and I don't remember how many points are here, this, using this empirical interpolation, and what we obtain is this function. And more importantly, what we get is basically that the error is 10 to the minus 5 and it's distributed in this way. So it's a fairly robust way of evaluating nonlinear functions using very few evaluations over the whole domain. And so, for example, we applied it to many problems, and as before, now we treat each of these snapshots of a nonlinear function as being the space in which we have to project. And so we look at the singular values, and the singular values decay very fast again. and the way the basis functions look like for the mobility are, for example, this. So what we have done next is basically couple doing dynamic mode decomposition and DEIM. And again, what we have to do is evaluate from the given some input parameters, we basically compute whole solutions. From these whole solutions, we evaluate either DEIM functions for where we're going to evaluate the functions, and DMD and POD basis. And then we just put them together to be able to compute, for example, this basically saturation equation with Darcy's law, which contains a mobility. And this is the 5-point case of the SPE again. Basically, these are the details of the simulation I showed before, some slides. Oops. OK. Well, this was supposed to be showing the results of a simulation. And what we end up doing is basically we use a mixed multiscale finite element. And we use a sequential approach in which we do the pressure equation, we solve it on a coarse grid, and the saturation, we solve it implicitly on a fine grid. So the way we build mixed finite elements, I'm showing the slides because I want to describe a little bit the method. So what we end up doing is, again, we have to solve this problem where this coefficient may have significant variance over the domain. And what we end up doing is we have the coarse problem in which we have to impose basically for each of these segments, we will impose a flux 1, constant pressure on both sides, and solve each of these problems to capture snapshots. And from these snapshots, we'll basically construct the multiscale finite basis functions. And as before, from the snapshots, we will basically solve an eigenvalue problem that corresponds to the mass matrix. If the mass matrix is evaluated this way, that is putting the inverse of the coefficient and just the jumps on the pressure, we'll basically obtain the dominant eigenvalues in which we will describe the velocity, and the pressure are going to be piecewise constants over the Coarse scale. So what we do now is basically using this discretization, we'll try to come up with an input-output parameterization that has a POD to describe input-output, and DEIM to reduce the number of evaluations we have to do over the whole domain. And so what we have found is that, for example, we can retrieve discretizations in which we can use only 2 POD modes and 20 DEIM evaluations and get order 5% error for a single phase flow. Before I was showing for a 2-phase flow. So we can also adapt this for a 2-phase flow, and I'm going to show it later. But first, let me show the kind of things we're trying to do, which is basically in oil industry, what they need to understand is, for example, if I have a set of injectors and a set of producers, if I change the injection rate somewhere, or I change the pressure, the valve I allow the outflow to go on one of the producers, what will be the effect on production? For example, in Saudi Arabia, they have a slightly different problem than most of other oil companies in the sense that Saudi Arabia basically owns the fields for eternity. And they have estimates that they're going to be producing in 200 years still oil. So at the production rate that they have right now. So they don't really care about how much oil they can get as fast as possible, but rather they care about getting most of the oil out. And so their goal is really, how can we optimize production, not only given the prior data, but really on a day-to-day basis. And so what we are striving to do is basically develop, for example, using the red lines of injection rates on different producers and different injectors, we want to understand our production. And then what we want to do is see if, by perturbing boundary conditions, that is, we computed everything given boundary conditions, that is, injection rates, coefficient distributions, and production rates. And now we want to perturb these production rates and understand if the system is robust. And what we have found is that the system is fairly robust, and it's fairly our prediction is fairly insensitive to the production rate. That is, we can use our reduced order models, that is, this proportional decomposition and discrete empirical interpolation methods, to use a few degrees of freedom and still get fairly accurate representations of the behavior of the system. Similarly, another important thing for oil companies is understand the net present value of the reservoir. That is, how much oil is there that I'll be able to extract. And so what they end up doing is very high fidelity simulations of injection rates and distributions of producers and injectors, and see how much oil they can extract. And with that, and obviously some cooking, they give a value to each of the reservoirs. And so what we are trying to do is develop reduced order models that can be robust enough to give good representations of the problem, even while using much fewer degrees of freedom. And in addition, surprisingly here, we don't have a good explanation for, we converge faster to the result than the fully resolved system. It may be because optimization may be using too many degrees of freedom here. It's not really clear. So the next thing we have been doing also is testing how dynamic mode decomposition behaves with DEIM. And basically the way we see it is, as before, we're doing a compressible flow and with a permeability coefficient that is nonlinear in the sense of an exponential. And this is odd. Anyway. So what we see is, for example, how basically this is a prediction with DMD, that is fully computed DMD, evaluating everywhere in the domain the residuals and the Jacobians, and how DMD DEIM improves as we increase the number of evaluations. But what you see here is that basically once we reach about 80 points, you cannot tell the difference between having the full model and the reduced evaluation of the residuals. But what you see here is a difference in cost. So here is about here. So it's about 7 times cheaper to evaluate DMD combined with DEIM. And the prediction is very robust too. So we have extended this empirical interpolation not only to do global interpolation, but rather to couple it with local evaluations. That is, we are going to change the way we evaluate the local problem, the inner product of the local problem, by changing the quadrature, by using this discrete empirical interpolation. And to do so, we basically still have to be able to prove that our coarse representation is going to be able to bound the error of the fine representation. So this involved quite a bit of work to be able to prove it, but we started testing it and immediately we saw excellent results, so then we had to have a reason as to why this was working. So at the end of the day, what we want to do is be able to evaluate the fine, on the fine grid, the residual from the coarse problem. And then evaluate the Jacobian also on the fine grid, given the coarse problem of the multiscale finite element, but we want to do so cheaply, in the sense of something that scales like the number of degrees of freedom we have in the coarse mesh. Not like it happens right now in the fine mesh, that everything scales like the fine mesh, period. So the way we go about it is basically we'll compute the residual snapshots locally to each of the elements, and basically we'll try to define the spatial points in which we have to evaluate this residual to minimize the cost. And to do so, basically we do a partition of the problem into coarse regions, and then we solve a particular or proportional decomposition to obtain the coefficients. So basically we have to weight appropriately with the discontinuous coefficients. Because if you use the conventional L2 inner product that DEIM uses, basically what will happen is that you will not have control over the fine problem by just evaluating over the coarse problem. And this was basically, once we had this insight, it was fairly easy to explain why the DEIM algorithm works, and basically the construction of Sorensen basically goes through. So many of the things we're doing, basically we try to get global, that is input-output models, to a certain precision, say 5%, 10% error. So what we need to do is basically control the local error such that it's always smaller than the global error, but we don't want more local error, that is what the discretization is giving you, such that this is machine precision and this is only 10%. So we try to balance both errors such that this one is the driver and this one is controlled such that is always smaller than that one and does not protrude. So the way we have gone about it is basically we can try basically an academic test case in which we put these inclusions or these inclusions. And for a nonlinear problem, we basically end up finding that the black dots in these plots, I'm not sure if everybody can see them, is where we end up evaluating the quadrature. And what it boils down to is we end up putting basically 2 quadrature points per element. And each of these elements in particular in this case had 100 degrees of freedom. So with very few evaluations that basically scale like the number of degrees of freedom. So we have 1 degree of freedom per block, and we are evaluating on each of the blocks twice. We can get sufficiently accurate representations, as you can see in the decay. So basically this is explaining what I have been mentioning before, that is, we want to evaluate in the offline case, that is before we try to go to solve real problems for engineering applications. We try to obtain all the snapshots that we need to be able to evaluate the core scales for multiscale finite elements, the discrete empirical interpolation points for evaluating the residuals and the Jacobians. In addition, we also want to get the global evaluation of the DEIM points, because we don't want to go back to the coarse mesh everywhere and evaluate everything again. So we need to have global DEIM evaluation and local DEIM evaluation. And all these things we do offline, such that once we are online, we just need to project onto a space. And basically, this is the idea. And as before, we end up going from the fine scale to the coarse scale, and from the coarse scale to the very reduced scale. And so let me show you how this works. And basically, the same kind of problems as we had before. Basically, for example, this permeability distribution with this coefficient multiplying the permissivity. We see that we can evaluate with 3 local DEIM points of each coarse block and 5 global DEIM points to evaluate the global modes. We can get a fairly accurate representation that is 5% with 5 points. So this is basically, once we have the difference between the reference solution, that is the full-scale multiscale finite element discretization, against this multiscale with few evaluations and a global representation with only POD modes, with 2 POD global modes, basically we get fairly accurate representations. So given that it's already 5 o'clock, I'm going to skip the discussion of the influence between doing the global and the local onto the global and so forth. And let me conclude with, let me skip this and basically show you, basically we have been doing 3D representations of these kind of simulations, which is again, mixed finite elements where we go and do multi-phase flow. As before, we solve the pressure equation with the projected modes, and we project them to a velocity which is mass conservative. And we do not change the multiscale basis functions once we have started the computation. So that is, we compute them offline and then we use them online without changing them. And you can see the effects of basically enrichment. So this is a full multiscale simulation. If we only put 2 basis functions per edge, this is a mixed finite element, so we put 2 basis functions per edge of the velocity field, we get this reconstruction. If we put 4 basis functions, we get this kind of reconstruction, and we can do the same kind of approach for 3D simulations, using a full-scale simulation or a mixed multiscale finite element. And now what we're trying to do is basically come with global representations of these kind of solutions. I'm going to skip this. So to conclude, basically, I'm going to reiterate what I said before. Our goal is to be able to reproduce with as few evaluations as possible robustly the behavior of complex systems. And to do so, we basically have decided that the best way to tackle that is break the problem into what can we do at the local level, what kind of approximations can we do locally, what kind of approximations can we do globally, how do we make them interact with each other in a non-intrusive, in a way that does not pollute the final outcome, and do that robustly. And our goal is basically to start doing uncertainty quantification, mostly optimization studies and history matching or data assimilation for reservoirs, oil reservoirs mostly. Thank you.